Hi, I'm Atul and I'm in London right now.
Hi, I'm Paul and I'm in Burnley, Lancashire right now. Okay, so today we're going to have a look at KP problems. So KP is the equilibrium constant when we're looking at gases, and as opposed to Kc when, well, we can be looking at gases or liquids and we're calculating concentrations. Here we're going to be calculating partial pressures. So we follow the same method we've used for Kc, which we've looked at before, is using the ICE method. So where this is the initial moles, change in moles, and equilibrium moles. So initially this will look like exactly we do for Kc. So putting in the information from the question, we're starting with 2 moles of A, the same, 2 moles of B, and at the start with nothing of C. And then we're told the equilibrium mixture was found to contain 0.9 moles of A. So we can put that in, 0.9 moles of A. So we can see the change in moles there is 1.1. So 2 take 1.1 gives us 0.9. Now the change for B, because it's a 2-to-1 ratio from A to B, would be half of that. So that would be minus 0.55. And the change for C would be 3 times the change of B, which is 3 times 0.55, which I make to be 1.65. And because that's a product, that's an increase of 1.65. So for C at equilibrium, we'll have 1.65 moles. And for B, to take 0.55 would have 1.45 moles of B. Now, if we write our equation for Kp, then it's products over reactants, but partial pressures of products over reactants. So we'd have the partial pressure of C, put it in brackets, cubed. So it's raised to the power of the moles in the equation, over the reactants, which is the partial pressure of A squared times by the partial pressure of B. And then we need our equations for partial pressures. So partial pressure is mole fraction times the total pressure. So if we add up these moles, we'll be able to work out the mole fraction. So 1.45, 1.65 would be 3.1. At the 0.9 would be 4 moles. So our mole fraction is the moles of our reactant and product divided by the total moles. So put MF for mole fraction. So for this it would be 0.9 over 4. Which is 0.225. And then 1.45 over 4 is 0.3625. And 1.65 divided by 4 is 0.4125. And then times by the total pressure. So it hasn't given us the total pressure, so we can just write in P there for our total pressure, or PT. And we'll see what happens to that when we put that in the calculation. So Kp equals the partial pressure of C cubed, so that's 0.4125 times by the total pressure cubed over partial pressure of A, 0.225, and that's squared, times by 0.3625. And we can see there we've got PT cubed on the top and PT squared and PT on the bottom. So on the bottom we've got PT cubed, and on the top we've got PT cubed, so we can cancel the PTs. And then if we put that, that should come out at 3.8 to two significant figures. And then the units, well, if we put the units in instead of numbers, so we'd get Kp is, let's say the pressure was in pascals, so pascals cubed over pascals squared times pascals, and we see, just like the total pressure cancels, the units would cancel, so here we'd have no units. So our answer for Kp is 3.8, no units.
Dimensionless.
Exactly.
Yeah, great. And while you were doing that, I was also wondering what happens. I mean, we don't know the total pressure, and it happens to be the case that because there's a cube there, I'll just do some pointing there. There's a cube there, a square, and one there. The pressure does actually obviously cancel out due to equivalent fractions.
Yeah.
But what would happen if it didn't? I mean, if the numbers were not favorable for that to happen?
Yeah, then you for the partial pressures you put in you times by the actual pressures here. So you would times all these by 500, and you'd be given the pressure in the question.
Of course, yeah. So in this, they don't happen to give the pressure because it ends up being inconsequential. But if they did, yeah, okay, that makes sense. And what's this measure of Kp? Is just like a pressure measure of moles. It's just like Kc, I suppose. With
yeah, exactly. It's like Kc. It shows you where the equilibrium lies for the reaction. So if it's bigger than 1, then the equilibrium lies to the right, so towards C in this case. And if it was less than 1, the equilibrium would be lying to the left, or favouring A and B in this case.
Great, yeah, good to see that. Also with gases, look forward to whatever the next one is.
Okay, thanks, Cecil.
All right, cheers, bye-bye.
Thanks. Bye.